We're going to be talking about antiderivatives. This is the end of chapter 4 before we get into chapter 5. So I kind of lump it together with the chapter 5 material on integration, and you'll see why I'm going to make that leap. First of all, we want to find functions. Get a highlighter here. So we want to find functions f, or a function f, whose derivative is a known function lowercase f. So we are looking at finding functions. Correct that grammatical error here. Let's write that out. So let's work backwards here. So we use a think cycle. If we're going to find antiderivatives, it's kind of reversing the process. So if you look up here, if I want to find the antiderivative of something, then whatever that something is, if I take the derivative of it, I'll get to this side. So we're going to just reverse the process. So if I'm looking at what I call a think cycle, fill in the think cycles below by thinking backwards. If I'm going to look for an antiderivative of secant tan x, then whatever it is, if I take the derivative, it'll be secant tan x. So if you look at this, the derivative of secant x is secant tan x. So that means that the antiderivative of secant tan x is secant x. Doing the same thing, if I'm looking for the antiderivative of cosine x, whatever goes in the rectangle here, if I took the derivative of that, I would get cosine. And obviously, you know that that's going to be sine x. Okay, so just thinking backwards. So I know an antiderivative of cosine is sine. So if I come down here to x squared, then if I'm looking for an antiderivative of x squared, then I'm thinking that whatever goes in the rectangle, then if I take the derivative of that, it's going to be x squared. Now, obviously, we know a little bit at this point about our derivatives. So we know that the power of the derivative, the power of the function drops 1 when we take the derivative. I just don't know what the constant is out front, so I'm going to make that an ax cubed. So then I'm going to take the derivative. I'm saying I'm going to let f of x equal ax cubed, therefore f prime of x is then equal to 3ax squared. So then, if I look at this, that's my derivative of from ax cubed. So I've got x squared. So I'm going to then set x squared equal to 3ax squared. And then dividing both sides or canceling the x squareds, I get 1 is equal to 3a. And you can see that a is equal to 1/3. So a being equal to 1/3 would then make f of x equal to 1/3 x cubed. So we would say an antiderivative of x squared would be 1/3 x cubed. Okay, so if we look at the formal definition then, now we just found an antiderivative. I'm going to label it f to go along with what we're looking at down in the definition. So a function f is called an antiderivative of a lowercase f function on an interval I if f prime of x is equal to lowercase f of x. So remember, an antiderivative we had was 1/3 x cubed. So if I look at this, if I look at f prime, I can take this and I can say, well, then that would mean that 1/3 times 3x to the 3 minus 1 power would be equal to f of x, lowercase f of x. So if I look at this, this is just going to be x squared is equal to our function. So f prime is equal to capital F prime of x is equal to f of x for all x in the interval I. Now we'll have a few more of these, but let's progress. And we have another theorem. So if f is an antiderivative of lowercase f on an interval I, then the most general antiderivative of lowercase f on that interval I is f of x plus c, where c is an arbitrary constant. So if we find the most general antiderivative of these three functions, then we're going to look at our antiderivative of sine. So, and you know, if you're looking at doing a think cycle, maybe pause for a second. So remember, sine is a known derivative of some functions. So you know it's not just going to be cosine, because the derivative of cosine would be negative sine, sorry. But I know that I have to have a negative sign from it. Now the derivative of negative cosine would be positive sine. So the antiderivative of sine is going to be negative cosine. So take those away. Okay, so negative cosine x, and then we would just add a plus c. So recall, let's do a little check on that. If we look at f prime of x then is equal to, well, the derivative of negative cosine then is sine x, and then the derivative of c is just 0. So it kind of checks out that this is equal to f of x. So let's look at b. So then for b, now remember you've got f of x is equal to, you've got to go up a power, so that's going to be x to the n plus 1 over n plus 1. And then we'll put the arbitrary constant c. So let's address this issue with the derivative then, and it's kind of getting at one of the rules we've already talked about, but we have f prime of x is equal to then, if I look at this, it's going to be, take the power out front, so you're going to end up with n plus 1 times x to the n power over n plus 1 plus the 0, because the derivative of the constant is just 0. Cancel those, so we get f prime of x here is then equal to x to the n, which is equal to our original lowercase f of x. So going backwards and forth. So if we look at the third one, using that rule, then if we have f of x, there are times where we want to say, okay, I'm going to rewrite this using negative exponents. F of x is equal to x to the negative third power. Lowercase f of x being the function, the antiderivative then, f of x, capital F of x, is equal to x to the negative 3 plus 1 over negative 3 plus 1. You have to remember you're dealing with negative exponents now. So then we have capital F of x is equal to, let me see if I can find some room here. Capital F of x is equal to, we're going to rewrite this then as x to the negative 2, so this will be negative 1 over 2x to the negative 2 power, and there would be a plus c, the arbitrary constant. Now for that one, if I got back to the original function by taking the derivative, you would find that you would have f of x is equal to 1 over x cubed. Okay, so putting this together in a table, so we have a function f of x and a particular antiderivative that we'll talk about. So if I'm looking at a function c times f of x, the rule is that when we find the antiderivative, it'll just be c times capital F of x. The c goes along for the ride. If I have a sum, and I'll put a difference in here too, and I want to find the particular antiderivative, the rule would be that we would find the antiderivative of lowercase f, and that would be uppercase f, plus or minus the antiderivative of lowercase g of x, which would be capital G of x. Some type of designation that capitals are then the antiderivative, where the lowercases are the original function. So then if I have x to the n power in the next one, then I've got x to the n plus 1 over n plus 1. Now I'm leaving the plus c here. I'm just doing a particular antiderivative. And if I find the antiderivative of cosine, I have sine. Remember, if you do your think cycle with the sines and the cosines, the derivative of sine would take you back to the function cosine. Then you have cosecant x, cotangent x. So cosecant x, the derivative of cosecant x is actually negative cosecant cotangent, but we want the antiderivative of the positive cosecant cotangent, so that will then be negative cosecant x. And then for e to the x is pretty cool because its antiderivative is just e to the x. And then with 1 over x, the antiderivative is ln of the absolute value of x. Okay, so again, using your think cycle as you go through. And we have time for one more example. So if I have g prime of x is equal to 4 sine x plus 2x to the 5th minus square root of x over x, the first thing that I'm going to do is I'm going to try to simplify things a little bit because I want to go back to the function. I'm going to do that by undoing the derivative and getting the antiderivative. So I have the following. I have g of x then would be equal to the antiderivative of, and I'm going to write it like this for right now without any kind of fancy notation. It would be an antiderivative of 4 sine x plus, I'm going to see this as a fraction, and I'm going to write this as 2x to the 5th over x minus, then I have x to the 1/2 over x. I want to take the antiderivative of that expression. So now I've got g of x is equal to, I want to take the antiderivative of 4 sine x, and I'm going to do some simplifications here. So I have plus 2x to the 4th power, and then I have minus x to the negative 1/2. Remember your exponent rules. Okay, so I'm going to take the antiderivative of those expressions. I'm going to move things around. Erase a little bit here and move things up. Okay, and so that's what we're looking for, the antiderivative of that expression. So I have g of x then is equal to, so the antiderivative of 4 sine x would be, keep the constant, remember, and then it would be negative cosine x plus, then I have a 2, leave the constant, carry it with you, x to the 5th power, 4 plus 1, over 4 plus 1, minus x to the negative 1/2 plus 1, which would be positive 1/2, over positive 1/2. And then with the plus the arbitrary constant c. So we get g of x is equal to negative 4 cosine x plus 2/5 x to the 5th minus 2, and we take the square root, or the x to the 1/2, and make it the square root of x plus c. So we get a function g of x is equal to negative 4 cosine x plus 2/5 x to the 5th minus 2 square root of x plus c. That's enough for the first video, and we'll sign off here, and we'll come back to section 410, example 3.